In architectural acoustics, everything changes once a sound wave drops below what we call the Schroeder cutoff frequency. Below this threshold, sound stops acting like straight geometric rays and starts behaving as massive, discrete waves that bounce between walls to create overlapping standing wave patterns, or room modes. To understand how to control these heavy, low frequencies, we first need to isolate them. Imagine a loudspeaker suspended in the dead center of an infinite, empty void. In this limitless environment, the sound expands as a perfect sphere, pushing energy outward evenly in all directions, a complete 4-pi steradian radiation. Because it isn't bouncing off of any walls or floors, there is absolutely zero acoustic boost added to the sound. This pristine, untouched sphere represents our absolute acoustic baseline. It's how sound behaves before architectural geometry gets involved. Now let's take that same speaker and slide it right up against a solid wall. Suddenly, the entire acoustic environment shifts. The physical boundary blocks the rearward sound, restricting the radiation angle to a 2-pi steradian hemisphere. All that trapped energy has to go somewhere. By forcing the output into half the physical space, the speaker's acoustic power effectively doubles, yielding an immediate 3-decibel boost in low-frequency sound pressure. But something else happens at this boundary. Sound travels by physically bumping air molecules together. When moving molecules hit rigid drywall, they have nowhere to go. The wave's particle velocity drops to zero. But you can't delete that momentum. As velocity flatlines against the surface, the kinetic force compresses, pushing acoustic sound pressure to its absolute maximum. This anatomical fracture of the wave explains why gluing cheap, porous foam flat against your walls does absolutely nothing for bass. Fibrous absorbers work by causing moving air particles to rub against their threads to create friction. If the air velocity at the wall is zero, there is simply no movement to absorb. If a wall complicates sound, the true choke point lies where 3 boundaries meet, the trihedral corner, where 2 walls intersect the floor. This maps how restricting radiation angle manipulates power. Confining sound to a 1/8 space forces an 18-decibel spike in low-frequency pressure. Compare that extreme corner peak back to the 0-decibel baseline of our floating speaker in free space. The geometry actively multiplies the bass. This intense 18-decibel bottleneck happens because of a mechanical reality known as universal modal termination. When sound waves bounce back and forth between parallel surfaces in a rectangular room, they create overlapping stationary modes. Every one of these standing waves, whether bouncing wall to wall, floor to ceiling, or diagonally, physically anchors and terminates deep in the corners of the space. By forcing every mode to converge in one spot, these trihedral intersections become extreme low-frequency pressure cookers. But this exact concentration creates a strategic vulnerability. Placing dense acoustic treatments right in those highly pressurized zones allows you to extract maximum energy from multiple room modes all at once. To attack these dense pressure zones, engineers often deploy resonant absorbers, sealed diaphragms and membranes that act like a mechanical spring and mass. Because they respond directly to pressure changes, they are mounted flush against the boundary walls where pressure is highest. But there is another, highly spatial solution for taming low frequencies, the quarter-wavelength bass trap. It relies on a specific quirk of wave physics. If air particle velocity is completely stationary at the rigid rear wall of a sealed cavity, it is forced to reach its absolute maximum exactly 1/4 of a wavelength away from that surface. By placing a semi-rigid, porous fiberglass board directly across this high-velocity opening, the rapidly vibrating air molecules are forced through the dense fibers. The intense friction generated here efficiently converts the kinetic wave energy straight into heat. Because the trap is aggressively converting movement into heat at its open mouth, the actual acoustic sound pressure directly in front of the device drops towards zero. This creates a localized pressure differential, an acoustic void that physically draws adjacent low-frequency energy directly into the opening. This localized vacuum effect means a carefully placed quarter-wavelength trap absorbs a significantly larger footprint of sound energy than the physical dimensions of its front panel would suggest. Of course, heavily trapping a room can accidentally suck the life out of the mid and high frequencies. That's why hybrid solutions like the Corner Killer deploy thick absorptive material against the walls, while facing a rigid wooden diffuser toward the room. The hidden fiberglass guts quietly eat the low-frequency pressure nodes, while the hard, math-based surface scatters incoming trouble, preserving the natural sparkle and liveliness of the space. Mastering the acoustics of a space requires looking past the top-line dimensions. By mapping the exact geography of sound waves, we turn a room's own intersecting boundaries into the perfect trap to defeat the physics of sound.